Hey everyone, and thank you for joining the AstrumDrive podcast. So today, as usual, we're going to review what we did in the last sprint, and we're going to check what we're going to do in the next sprint, sprint 7. So today we're joined by Nelson Bolivar. He's the head of our physics department. So Nelson, as usual, the stage is yours. Can you please give us a short overview? What did we achieve in sprint 6?
Thank you, Vilo. Hello, everyone. Sure, this sprint was very interesting. The last one, I mean, the one that we're talking about right now, and of course, is tightly connected with the sprint that we're currently working in, which is really interesting. Let me give you a brief review of what we did so far. We've been working uh, on our metric, I mean, our proposal of a metric that has some spherical symmetry and it's a time independent work. And this proposal, what we want with this metric, specifically right now, we're looking for easy ways to incorporate matter that can help us to see which relations we can use in order to remove some of these peculiarities that we have with negative density energy and so on that you people know already about this. So basically, what we're doing is reproducing some of the few articles that we've been studying during the last sprints, articles, the recent articles, the published articles, and how the way they figure out how to obtain information from already known warp drive metrics, which are basically Alcubierre's metric and Natarius metric. And using these tools, we figured out a way to find more information. One of the things is to find Einstein's equations and find constraints between the parameters in Einstein's equations, in this case with the velocity, constant velocity. And other thing is finding this other type of equations that appears. For instance, there is this type of equation that appears in Alcubierre's uh, that when you take one part of Einstein's equations, which are we call Borger equations, like because this similar, quite similar to the differential equation that describes shock waves in fluid dynamics. So it's very interesting to see if we could find this type of equation, and we did. We find an equation similar to this, but it has does not allow for diffusion and it's not and it's also a non-homogeneous, which is a bit different to what people have found. But just slightly different. We didn't solve this equation because wanted to last sprint is that we looked into the all Einstein's equations with some modified energy momentum tensor using our metric, the spherical symmetric metric, and see which type of fluid we can put in if we allowed, for instance, anisotropies, we are allowed to put, for example, diffusion, some dissipation terms, and we found that uh, we can put anisotropies, which is okay, very nice, but we are not allowed to put anything that uh, mimics or that can model fluxes or dissipation or even heat fluxes in the system, not in the current way that is described the model. I mean, so basically, what we're achieving, what is easier, because this is not looks like a very new. What we're doing is like it's very easy to see when you have a spherical symmetry. It's very easy to see where you can put put this specific terms that I'm going to describe, for instance, heat fluxes and so on. And it's easy now to see, oh, we are not allowed to put these terms on the other. So as it is now, the matrix only allows anisotropies, which is also interesting. But we know, which is part of what we're working on during the sprint, we know or we suspect what is it that we need to modify in the metric to look for solutions that will allow us to put, for example, these heat fluxes. One other thing that we did, and it's quite interesting. we we've been reviewing an article. This it, it, they made a classification last year of word drive. This is a very nice article. I really recommend, guys, if you read as the authors Bobrick et al. Uh, and in this article, they classify the metrics that the word drive is in fact as four classes of word drive. And the classification goes on taking into account which observers are inside the word bubble, outside the word bubble, and how they connect to each other. There is a mapping that we call, and how it basically saying how the mapping that we call is, let's say, for example, that two observers inside the bubble or outside the bubble sees, for example, that they have the same time or not measuring the same time, or if they have, for example, some connection that is, for example, a Lorentz transformation that connected to, or it's another type of transformation. Basically, this is what we're calling a map between the observers. And using these observers, we are using a couple of observers outside and one observer inside, and they move a specific velocity with respect to a third observer. And using this velocity and this mapping, you can have a classification of how each warp should be. And they found out that they can put everything together basically in four. Sorry. And these four are basically like two superluminals and two that are subluminals. And these are like very subluminal, something that is moving, let's call it that way, and then something like mild superluminal, which is okay, moving faster than the speed of light, but that's it's not that fast. And the same way, basically, with the subluminal cases. What they found in these cases, which is make it very interesting, is when you use this classification, you define very clearly what you expect to have in a word drive metric. And so using these guys' proposals, basically what a word drive is just a bubble, in a sense, that has servers inside and outside. And this is the main mechanisms that you can use. And of course, not all word drive metrics will fall in all classifications and the four classes. And where they find, for example, the Cupier's goes into some specific class, it's a class 2, class 4, and these are very interesting because in these classes, let's use Cuvier's example. These classes, once you work out a bit what is going on physically with Einstein's equations, and a scenario, you find that why is it that perhaps there is a suggestion? Why is it that you perhaps need negative energy? And it's because you need, for consistency with Einstein's equations, that some terms will have to cancel each other. So basically, you need negative energy to cancel out some stuff inside the equations that will give you the right answer. The right answer means consistent with Einstein's equations. So this is a suggestion that we might we might have a clue here with what it could mean, this presence of negative energy in the known solutions we have of word drive metrics. And also we give us a clue how to solve this problem and try to work it out and obtain positive solutions. They do, in fact, they work around a bit with the solutions. Uh, so basically, we reviewed all this. We found some small differences between the calculations, probably some typos. Uh, but what we did was what we mapped some very nice stuff. We map some of the results to some more generic results that we are thinking of. that we can lead us to a more interesting matter configurations, which is what I was telling you just before. For example, if you make the 12 servers to have different times synchronicities, and the synchronization is not the same, so they measure in different times, this will impact on how the metric is constructed. And we find out that this construction is pretty much what we need to put more general structures in the in matter configurations in energy momentum tensor. This is basically what we are going to work later. Uh, well, basically, so we check all this stuff, and we check that you can do all these classifications using these public classifications. We went to what they call the general spherical symmetric warp, which is different to our general symmetric warp. Theirs are more like a general metric with a spherical symmetry, pretty much similar to uh, a general version of a Schwarzschild metric. And also they find that they suggest that the best way or the easiest way to look into the warp drive is using some axisymmetric configurations, which basically is that you have a cylinder symmetry, one direction for propagation, which is in the direction of the length of the cylinder, and that's a radial and angular coordinates. And they found out that using this, you can reproduce using some algorithm that they described in the paper. You can reproduce, for example, Alcubierre's case, which is very nice. And this is very nice because basically these guys found out what I'm now interpreting in a different way. And this interpretation is more like uh, you have some deformations that you have elements of the matrix, and each elements you're adding in the direction space space time is that you are adding some deformation to each. It's like adding a term. Of course, this term is not whatever you want. It's in a specific way of deforming the space time in this direction. And so these deformations or perturbations, as you want to call it, this is a very nice way to think of warps, and we have to work out that later. It's part of what we're working right now. So basically, we did all this, and finally we added cosmological constant to our spherical symmetric terms. We find out that uh, uh, there are several equations that are now very non-trivial, and now we have to work on these equations and find out which are the matters configurations that these cosmological constants will allow us to put in, or which type of equations we find. The point is that cosmological constants may seem like trivial, like you're adding a constant to Einstein's equations, but when it enters into the equation, it mixes up everything. And you find that the differential equations now are quite different, and probably the solutions are very, very different. And you can have a lot of more freedom in the type of solutions you can find. And basically, that's what we did.
Excellent, Nelson. So, Nelson, I just want to sum some of my understanding about the things you said. So, you said that we're creating our own work metric, and the reason why we're creating our own is that the Alcubierre metric, it has several issues. For example, it requires huge amounts of negative energy. So it is mathematically correct, but it's not physical in the sense that we cannot really build it in our physical world because we don't have good idea what is negative energy, and so we're very far away from creating tons of negative energy which are required for his solution. Because of that, we're approaching our own solutions for Einstein equations and warp drive metrics. And currently, the metric we found, uh, the semi-spherical metric you described, we're trying to resolve several things for this metric. So first, we want to see, is there a situation in which we can have this metric with positive energy, so we can uh, have everything with positive energy, so we are not going to need negative energy. The second thing is we're going to test the metric. Is it supporting super luminous speeds faster than the speed of light? Something we're going to do in the next sprint. And the third thing, very interesting, you said, is that we're trying to have the heat dissipation equations in this metric. And the reason why is that when we create the warp bubble, by having these equations, we can see a ways for this bubble to dissolve, because we want to create it, but we want to have a way to dissolve it. Is this correct understanding? Do you have anything to add or change?
The pretty much is quite about right. I think the only thing I want to add, I would like to say, is that first, let me go to the first things you said. Yes, we are using this metric because we want to solve those problems that appears in the construction that Alcubierre did, and then all the guys follow Natarios and some other modifications that appears during the time to, for example, remove these larger amounts of negative energy you need, but anyway, still have small amounts, and there are other modifications, but they all seems to need negative energy, which, by the way, is also a way to say that there's are violating some of the energy conditions, which we find out, and I think we did tell this to you guys during the previous sprints, the previous recording, is that we find out that these violations are not quite true, in a sense of that under Einstein's equations, you have constraints that will tell you that not all these violations are true, but some are true. And this is something that we will publish probably very soon. Uh, but anyway, anyhow, what we're looking now is like a generalization of the Alcubierre's form, the Alcubierre's metric, to gave it a spherical symmetric way, a form more spherical, not spherical in the sense of the bubble, because the Cuvier's bubble was already symmetrical, spherically symmetrical, but in the sense of the coordinates that are describing the space-time. And so using this is was at the beginning like a toy model. We call it a toy model as some specific proposal that you don't think is going to solve all your problems, but you think is going to give you some addressing you in the right direction, to tell you, oh, this is not working, this is like this, these calculations give you negative energy, this one seems like not, and then you start tuning up this proposal or changing everything, just change everything, but it gives you some direction. But by now it's like it's very helpful, not only for doing this, it's very helpful because it's easier to put matter when you have, it's what very well known how to put matter when you have this way of writing in a spherical symmetry, the metrics. uh, so what we found is like, yes, we had something that is quite similar to Alcubierre in one way, but also on another way, it's easier to see how matter comes in and which terms are not allowed. Then that to give us some clue as, okay, so we cannot use this, for example, as you well said, we cannot use dissipation or heat fluxes or stuff like that, but we can see more or less clearly what is missing. What is it what we need to put in the metric to allow for this type of matter in the other side of Einstein's equations? And then, of course, you have to work this out and see what are the constraints that appear to be consistent with our previous work, and see what happens with energy conditions and so on. So we find out that using this spherical symmetric way of writing, we find out this pretty much the same stuff we found before, which is that you don't have, now it's not easy to see how energy conditions are fulfilled or not, because the equations are more complicated, and that's probably the reason that people don't work in this way. The questions are more complicated. It's not that easy to see, but we think they're most fulfilled pretty much the same. So this is going to give us some very good ideas of what is it that is going on here, what we need to put or to remove to 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 remove again this peculiarity of negative energy. That's one thing, and the other thing is yes, disconnect with the fact that we want to have a mechanisms for the bubble to have some type of dissipation or something like that, and we're looking into that uh, to see what happens. Also, the combinations between several type of energies that you can have. You can have matter, but which properties does matter have? You have heat. You can have electromagnetic fields. You can have some fluxes of matter. So you have rotations, for example, and all this changes a lot how the energy momentum tensor looks, and this means that the Einstein's tensor have to need to have some specific way. So if you can find a way that all these elements in the energy momentum tensors are allowed, you find in the equations that they play that these quantities play between each other, and the interplay between them is a very nice way to physically try to have to terms that can remove the negative contributions, and you can obtain just positive contributions, or maybe you have negative but you can cancel this negative out because, for example, you increase something else, and then we will see is that possible physically at all. But this is the first step to get something new and physically achievable, at least in theory. And yeah, this is the very first step. So basically, yeah, what you say is right. I just uh, make a bit more long explanation.
Very much, Nelson, for giving more clarity about that. So let's go to our current sprint and just actually not here, but um,
Yeah, and our current sprint, well, I named some of the things already. We are already working on this very interesting stuff. First, we're figuring out uh, what happens with when you put the cosmological constant, which is interesting. It's going to tell us pretty much something about some type of matter that you could even add in the energy momentum tensor. This is one thing that we are currently doing. Uh, well, this is one thing that Gabriel was doing. He says she will incorporate again next week. But and well, the other things that we're doing is like using this proposal from Bobrick. Uh, we have these classifications that I just told you, and we have this algorithm to construct the metrics. Uh, so basically, right now I'm checking how our metrics goes into this algorithm. If we can reproduce using what they propose, and so far it is like that, uh, and so we can know if we have something that is, for example, it looks like some version of Alcubierre. We can have it's our metric basically answering questions. It's our metric allowing faster than speed motion, or just slower than speed, means superluminal or subluminal. It's one question that we're already answering right now, probably today. And there are other questions, for example, that are more concerned of what happens when you have different mapping between the observers, which differentiate these metrics a lot with others. So these guys, Bobrix, they propose as a very simple transformation between two observers, one observer that is inside the bubble, one observer that is outside the bubble, and they both are moving together. So basically, it's like saying we have a bubble. Of course, we have somebody, something inside the bubble that is moving, of course, with the bubble. And then we have another observer outside that is moving again with the bubble. And these two observers are connected somehow. How they're connected? Well, you can say that they're measuring the same times, or they are not, or they have some Lorentz transformations that are connecting them. So you have some type of length transformations, for example. And depending of the mapping that you can put there, you have a different metric. So, and in the article, what Public did, I'm going to name just one that is very interesting, is that you say you don't have the same times. You have a transformation between those times. So the guy that is outside the bubble is measuring the time that is different from the guy that is inside the bubble. That means there has to be something gravitational in the middle that is changing the way the time is passes for each other. This is what we know. So we don't really care too much about what is it, this thing that is in the middle right now. We are going to care about the transformation only. If you say these are not the same times that are measuring, this implies you have to change something in the metric. When you change this, they found a metric, and they found that you obtain uh, the energy, the energy density, negative energy density you need, but this we have to figure out because we have to look for the constraints that they never look. But one thing that is more interesting, because there's something I have to say, is you usually guys when put this in Einstein's equations, they just put an energy momentum tensor that has only energy density there. It's the only thing that is in the energy momentum tensor. So if you want to complicate this, you have to look for all the Einstein's equations that can have pressures, that can have anisotropies and so on, and see what is it that it allows your metric to put there. And of course, you can put what your metric, your spacetime allows you to put, but you can put less. That's all right. Can easily understand some results, but this is not always the way. If you can have more complicated configurations that, of course, your spacetime allows you to do, and you will have some other physical interpretations. Then this, everybody knows this, but my point is like, if you put this time transformation between the observer inside and outside, then you find that the space-time is modified in a way. And well, just figure it out. This is something that we just already know. Is that this is equivalent to change something in the way you foliate space-time, which foliating means you split the space-time into layers, space layers, which each is on each other. There are all layers are all over each other, and each layer that is over each other represents a different time, and the layers are just space. And this is foliation that we call. You have a, a, a distance, which is a distance measured in time between each other. This is described in using a function that you call the lapse function. And this function is usually taken to be one, the unity, because it's more simple to work in that way. But what I found already is that if you put this uh, different times mapping between the observers, it is equivalent to have a lapse function that is not one. It's a function, and it depends of the coordinates. Depends of the shape, even of the shape of the bubble. So it's quite interesting because it is more complicated. We have to be a lot careful, but that's what we need. The first step of what we need, let's call it that way, to put new matter into the energy momentum tensor, and that's something that I think it too ahead, but that's something that we're doing right now, and that's something that we're going to do during the next couple of sprints probably, and it's very interesting. It's a very simple thing that you can change, and I think it will have a lot of consequences that have not been yet exploited in the community. And these articles are quite recent. I think people haven't noticed this, or just they're not working about this. But anyway, this is quite interesting. at least for us. I think it's going to be a major step to understand a bit more. And this, we think, will allow us putting this thing together and other configurations, Van Droberg and also others, uh, so have minimal amount of characteristic of features that can allow us for positive and a smaller amounts of energy. Well, finger crossed. We're working on that.
So thank you very much for the overview. Indeed, we're entering in some very interesting waters. Excellent. So, Nelson, before we close for today, is there anything else you want to say?
Well, as usual, please, if you are hearing this and you are interested in knowing more, ask questions, whatever, make suggestions. If you want us to talk about something about the work we're doing, ask us questions. And if you feel like supporting us, please do. And thank you.
Thank you very much, Nelson. And thanks to everyone who is listening this podcast. Thank you for your presence. And if you like it, please share it, subscribe to our channel. And if you want to support us on Patreon, we're sharing the link below. With that, thank you again for listening. And let me wish to all of you to have a very nice and successful week. Till the next time.